6 million light-years. If you have ever gone looking for the largest galaxy in the universe, that is the number that came back. One single object, nearly 60 times wider than the galaxy you're sitting in, 1 billion light-years away, so enormous it hardly seems like it should be permitted. That number has been repeated for 35 years, it is in textbooks, it is on every list of the biggest things in existence, and in July, a team took the deepest images anybody has ever taken of a single galaxy, and that number came apart in their hands. Not because the object turned out to be bigger than we thought, but because nobody had ever actually measured it. Not once. Not in 136 years. So what do you find when you finally go and check the size of the largest thing there is? Settle in. Subscribe if you have not, and stay with us, because by the end of tonight you will know exactly how large a galaxy can be, and why the part that defies explanation turns out not to be the size at all. Let's get into it. Part 1. The thing with no edge. You cannot measure a galaxy. I want to start there because it sounds like a trick and it is not one. It is a plain statement about the physical world, and once you have properly absorbed it, almost everything you have ever been told about the sizes of things in space becomes slightly unstable underneath you. Here is the problem. When you measure a table, you run a tape from one edge to the other, and the reason that works is that a table has edges. There is a place where wood becomes air, and the transition happens across a distance of approximately 0. The same is true of almost everything you have ever measured. Your height, a room, a car, a country, more or less. The physical world you live in is made of objects with boundaries, and the entire practice of measurement assumes those boundaries exist. A galaxy does not have one. What a galaxy has instead is a decline. Near the middle, the stars are packed relatively close together, and as you move outward, they get sparser, and they keep getting sparser smoothly, without any sudden change, without any last star standing at the perimeter with a sign, until eventually the density of stars in front of you is so low that you can no longer tell the difference between stars that belong to the galaxy and stars that happen to be drifting through the same region of space. There is no wall, there is no rim, there is no moment where you cross from inside to outside. There is only a gradient that thins until it becomes indistinguishable from nothing at all. Which means that every single photograph you have ever seen of a galaxy has been cropped. Not by the universe, by a person. Somebody looked at an image, decided where the interesting part stopped, and drew the boundary there. And every number you have ever read about how many light years across a galaxy is, including, I should say, the number for our own, is not a measurement of an object. It is a report on where a human being decided to stop counting. For most of the history of astronomy, this was an annoying philosophical footnote. Nobody lost sleep over it. You picked a convention, you applied it consistently, and you got on with your work. And then somebody asked the obvious follow-up question. If galaxies do not have edges, then how large can a galaxy actually get? What is the biggest one? And the moment you ask that, the footnote stops being a footnote, because there is no way to answer it. You cannot rank things by size if size is a matter of opinion. On the 16th of July, 2026, a paper appeared on the Archive preprint server, and it has since been accepted for publication in the journal Astronomy and Astrophysics. It is 20 pages long, it has 15 figures, and its title is not a statement, it is a question. The title of the paper is How Large Can Galaxies Be? The lead author is Carlos Marrero de la Rosa at the Instituto de Astrofísica de Canarias in the Canary Islands. There are 15 names on the author list, and 2 of them in particular are worth flagging, because they explain why this particular group was the one that did this particular thing. Ignacio Trujillo has spent the better part of a decade working on the problem of what a galaxy's edge physically is, not where it looks like it stops, but where something real happens. Mireia Montes has spent a comparable amount of time on the faint light that fills the space between galaxies and clusters, which turns out to be the exact thing that makes this measurement so hard. These are people who built a ruler, and then went looking for the largest thing in the sky to measure with it. What they measured is an object called IC 1101. If you have ever gone looking, casually, for the largest galaxy in the universe, that is the name that comes back. It sits at the center of a cluster of galaxies catalogued as Able 2029, roughly 1 billion light-years from here, in a patch of sky in the constellation Virgo, where there is, To the naked eye, absolutely nothing. It is not a beautiful object. It is not a famous photograph. It is a faint, featureless smudge of 13th magnitude, and amateur astronomers who go looking for it through backyard telescopes describe it, when they can find it at all, as extremely faint and very small. And the paper's opening premise is stated so plainly that it is easy to read past. The maximum physical extent that galaxies can reach, the authors write, is poorly understood. Not controversial, not disputed, poorly understood. Nobody knows how big a galaxy is allowed to get. Nobody knows whether there is a ceiling, and if there is one, nobody knows what sets it. There is no law in physics that says a galaxy must stop. There is no conservation principle that caps it. And the reason nobody knows is not that the question is unimportant. It is that until very recently nobody could measure a single one of these objects well enough to say where it ended. They also say something else, about the earlier attempts on this specific galaxy. Previous deep imaging, they write, confirmed its enormous extension, but did not indicate whether it has an edge at all. Sit with that phrasing for a second. People had already established that this thing is huge. What nobody had established is whether it stops. So they went and found out. They used a telescope on a volcanic ridge in the Canary Islands to take the deepest images anybody has ever taken of a single galaxy, and they pulled the answer out of light so faint that it is more than 1,000 times dimmer than the darkest sky on Earth. And that is what tonight is about. Not just the answer, though I will give you the answer, precisely, with the number attached before we are done. What tonight is really about is the question underneath it, the one the paper's title asks and the one that turns out to be much stranger than it looks. Where does the galaxy end, and where does the cluster begin? Because those two things, the galaxy and the enormous swarm of gravity and gas and darkness that it lives inside, are not separated by anything you could point at. They are made of the same material, they occupy the same space, and the boundary between them is not something you can go and look at. It is something somebody has to decide. I will also tell you now, so that you're not waiting for it in the wrong place, that the answer they got is smaller than the number you have probably heard. Considerably smaller. If you have ever read that this galaxy is around 6 million light-years across, that number is about to fall apart in your hands, and the way it falls apart is one of the better stories in modern astronomy. A real measurement, published in a real journal, by careful people who wrote down an honest warning that nobody ever read. But before any of that, before the telescope and before the number and before the three separate things about this galaxy that nobody can currently explain, there is the object itself. And the object has a history, and the history begins with an argument. It begins on a June night in 1890 in upstate New York with a 19-year-old boy at the eyepiece of a 16-inch telescope, looking at a faint grey nothing that would eventually turn out to be the largest thing anybody has ever measured, and being unable to agree with his own father about what he was looking at. Part 2. A Faint Smudge, June 1890. The 19th of June, 1890, Rochester, New York, new. The Warner Observatory, which was not a national facility or a university department, but a private observatory funded by a patent medicine millionaire named Hulbert Harrington Warner, who had made a fortune selling a product called Warner's Safe Cure and had decided to spend some of it on the sky. The telescope was a 16-inch refractor built by the Alvan Clark firm, which at that time made the finest lenses in the world. The man in charge of it was Lewis Swift, one of the great comet hunters of the 19th century, a man who discovered more than 1,000 new nebulae over his career, and who worked by a method that is almost impossible to imagine now. He would sweep. Point the telescope at a strip of sky, let the Earth carry the field slowly across the eyepiece, watch, and wait for something to drift through that did not look like a star. Then move the telescope slightly and sweep again. Night after night after night, in the cold, in the dark, with nothing but a human eye at the end of the optical chain. There was no photography involved in this kind of work. There was no detector. There was a man, a lens, and however much patience he had left. On this particular night, the eye at the eyepiece belonged to his son. Edward Swift was 19 years old, and he was working alongside his father, and at some point during that night's sweep, a faint grey smudge crossed the field of view. They found it. They agreed on that much, and then, according to the record, the telescope was moved, and afterward, the two of them could not agree on what they had seen, not on whether it was there, on what it looked like, Father and son, at the same eyepiece, on the same night, with the same instrument, produced two descriptions of the same object that did not match each other, and neither of them would concede. So Lewis Swift did something that reads, more than a century later, as an act of almost stubborn integrity. He published the position, he published the designation, and where the description should have gone, in his 9th catalogue of nebulae discovered at the Warner Observatory, entry number 47, there is nothing, a blank. He would not write down something he was not sure of, and he would not write down his son's version either, and so the entry went out into the world as a set of coordinates with no words attached. I want to let that sit for a moment, because of where this story ends up. The largest galaxy that anybody has ever properly measured, an object containing something on the order of 3.5 trillion stars, the single most extended stellar system in the known catalogue of the universe, entered the scientific record as a blank space in a list. Because a father and a son disagreed, and neither of them would give way. And there is a genuinely strange thing about that night that I think is worth saying out loud, because it is easy to skate past it. Neither of those two men had any way of knowing what they were looking at. In 1890, nobody knew that spiral nebulae were other galaxies. That question would not be settled for another 35 years, until Edwin Hubble found variable stars in Andromeda and proved that these faint smudges were separate systems, unthinkably far away. As far as Lewis and Edward Swift were concerned, they were arguing about a patch of luminous fog somewhere in the Milky Way. They had no concept of the object at all. The light landing on their retinas had left its source before there were animals with backbones on this planet, had crossed 1 billion light-years of empty space, had been focused by a piece of glass ground by hand in Cambridgeport, Massachusetts, and it produced a family argument about whether the smudge was round. The Warner Observatory itself did not last. Hulbert Warner lost his fortune in the financial panic of 1893, the observatory closed and Lewis Swift moved on to California. The great 16-inch Clark refractor was eventually sold. The catalogue entry, though, survived all of that, because catalogue entries are among the most durable things human beings make. 5 years later, in 1895, a Danish-Irish astronomer named John Lewis Emil Dreyer, working at Armagh Observatory in Ireland, published something called the Index Catalogue. Dreyer's job, and he was one of the great bookkeepers in the history of the field, was to gather up all the new nebulae that had been discovered since the last big catalogue, and give them permanent numbers. The first Index Catalogue covered discoveries from 1888 to 1894, and contained 1,520 objects. A second edition, in 1908, took the list up past 5,000. Swift's entry number 47 got folded into that first catalogue, and it came out the other side with the name it has carried ever since, IC 1101. Around 1900, an astronomer named Herbert Howe went back through the Index Catalogue objects, re-observing them and checking the entries. When he got to this one, he added a description. His description was extremely faint and very small, which is, I should point out, entirely correct. It is a matter of perspective. The object is 13th magnitude, which is roughly 250 times fainter than the faintest star a person with good eyesight can see on a dark night. Its catalogued angular size, the amount of sky it covers, is 1.2 arc-minutes by 0.6 arc-minutes. For comparison, the full moon is about 30 arc-minutes across. So this thing, the largest galaxy anybody has measured, takes up a patch of sky roughly 1/25th the width of the moon. It is also, incidentally, in a slightly awkward place. Its coordinates put it about 1 arc-minute of right ascension inside the boundary of the constellation Virgo, right up against the border with Serpens Caput, which is why, if you go looking for information about it, some sources will tell you it is in Virgo, and some will tell you it is in Serpens, and both of them are describing the same coordinates. Formally, by the boundaries the International Astronomical Union drew in 1930, it is in Virgo. Barely. And there is one more thing about the discovery worth mentioning, because it is a small preview of a much larger problem that this entire video is going to be about. If you look this galaxy up in certain popular references, you will be told that it was discovered by William Herschel on the 19th of June, 1790. That is a wonderful detail. Herschel was the greatest observer of his era, the man who discovered Uranus and effectively invented deep sky astronomy as a systematic practice, and it would be a lovely thing if he had found this object too. He did not. The date is off by exactly 100 years. Every object Herschel discovered is in the New General Catalogue, not the Index Catalogue, because the index catalogue by definition only covers discoveries made from 1888 onward. Herschel made no nebular discoveries at all in June of 1790. What happened is that somebody, somewhere, transcribed 1890 as 1790, and the error was picked up and repeated and cited and repeated again until it became one of the standard facts about this galaxy. Hold on to that. Because a century-scale typo about a discovery date is a small, harmless version of the thing that is about to happen to this object's size, and the size version was not harmless at all. It shaped what everybody believed about the largest galaxy in the universe for 35 years. But to understand how that happened, you first have to understand that IC 1101 is not really a solitary object at all. It is the centre of something much larger, and that something had to be catalogued too by a graduate student working alone with a magnifying glass. Part 3. The Cluster. It rules. In the early 1950s, a graduate student at the California Institute of Technology named George Abel was working on the Palomar Observatory Sky Survey, which was the most ambitious photographic project anybody had ever attempted. The idea was to photograph the entire northern sky, systematically, on glass plates, using a wide-field telescope at Palomar Mountain. It took years. It produced thousands of plates. And when it was done, there existed for the first time a single, uniform photographic record of everything visible from that latitude. Abel was one of the principal observers on the survey. He was also looking for a thesis topic, and what he decided to do was go through the red plates, the ones taken on a red-sensitive emulsion called 103AE, and find every place in the sky where galaxies were clumped together into a genuine cluster rather than a chance alignment. His equipment for this task was a magnifying lens, 3.5 power. He looked at plates through a hand lens, and he counted galaxies. He went through the whole survey once. Then, not satisfied, he went through it again, more carefully. And he laid down rules, because the whole point was to produce something objective rather than a list of things that happened to catch his eye. A cluster had to contain at least 50 galaxies within a 2-magnitude range of the third brightest member. Those 50 had to fall within a specific radius, defined so that it corresponded to the same physical size regardless of distance. The cluster had to sit in a distance range where the counting was reliable, and it had to be far enough from the plane of the Milky Way that our own galaxy's stars and dust were not confusing the picture. When he was finished, he had 2,712 rich clusters of galaxies. He published the catalogue in 1958 in the Astrophysical Journal Supplement series. It was his doctoral thesis. It is still in use today, 70 years later, and every one of those clusters is still known by the number he gave it. Abel later began a southern extension of the same work. He died in 1983, about a month after presenting an interim version of it, and colleagues finished it for him. The combined catalogue runs to 4,073 clusters. Entry number 2029 on his list is the one we care about. Abel 2029 is, by his own richness classification, a Class II cluster, which in his scheme means between 80 and 129 member galaxies counted by his criteria. In practice, with modern spectroscopy, the number is much higher. A comprehensive redshift survey has now confirmed more than 1,200 galaxies as genuine members of this cluster, moving with it, bound to it. It is also classified as Bautz-Morgan Type 1, which is a scheme that describes how much the cluster is dominated by its brightest member. Type 1 means overwhelmingly. There is one galaxy in the middle that is so much larger and brighter than everything else that the cluster's appearance is essentially defined by it. Here are the numbers for the cluster itself, and I want to go slowly through them, because the scale is the entire point. The total mass inside what astronomers call the virial radius is roughly 9.8 times 10 to the 14th solar masses. That is 980 trillion times the mass of the Sun, very close to a quadrillion solar masses. The virial radius itself, the region inside which the cluster can be treated as a settled bound system, is about 1.91 megaparsecs. That is a little over 6 million light-years in radius, which means the cluster is roughly 12 million light-years across as a gravitationally coherent object. The galaxies inside it are not sitting still. They are moving through the cluster at random in all directions, and the spread of their velocities, the number astronomers call the velocity dispersion, is 967 kilometers per second. Hold on to that figure. It becomes important later in a way you will not see coming. And then there is the gas. The space between the galaxies in Abell 2029 is not empty. It is filled with hydrogen and helium plasma that has been heated by falling into this gravitational well to somewhere between 7,500 and 8,500 electron volts of thermal energy, which translates to roughly 90 million Kelvin. That is around 6 times hotter than the core of the Sun. It glows in X-rays with a luminosity of about 9.5 times 10 to the 44th ergs per second, which, to give that a shape, is roughly 250 billion times the total energy output of the Sun across all wavelengths, radiated as X-rays alone, continuously. And here is the part that reorganizes how you should think about clusters. That hot gas outweighs all the stars in all the galaxies in the cluster combined, by a large factor. When you look at a picture of a galaxy cluster and see 100 bright smudges scattered across the frame, you're looking at the minority of the ordinary matter. Most of the normal matter is the glow you cannot see, filling the gaps. And even that is a minority overall because the whole thing, gas and galaxies together, makes up something like 15% of the mass, and the rest is dark matter. Abell 2029 is also what astronomers call a cool core cluster, which is a slightly misleading name for a real phenomenon. In the very centre, where the gas is densest, it radiates away its heat faster than the rest of the cluster can resupply it, and so the temperature drops, not to anything you would call cool, but from around 8,500 electron volts down toward 3. For a long time, the expectation was that gas in that state should be pouring inward and collapsing into new stars at a rate of hundreds of solar masses a year. It is not. Almost none of that predicted star formation is happening anywhere in these systems, and working out why has occupied a substantial fraction of a generation of X-ray astronomers. The leading answer involves the black hole at the centre, injecting just enough energy to keep the gas from cooling all the way down, which is a thing worth filing away, because we're going to come back to the black hole at the centre of this particular cluster, and it is not a small one. The whole system is about 1 billion light-years away. Its redshift is 0.077, which means it is receding from us at roughly 23,000 kilometers per second, 7.7% of the speed of light. The light we collect from it tonight left when the most complicated living things on Earth were still, for the most part, single cells in the ocean. And sitting at the exact centre of all of it is IC 1101. I mean that quite literally, and it is one of the more remarkable small facts in this story. Modern surveys have located the kinematic centre of Abell 2029, the point that the whole swarm of 1,200 galaxies is moving around, and IC 1101 sits on it within the measurement uncertainty. Its projected offset from that centre is 123 kiloparsecs plus or minus 170, which is a fancy way of saying it is indistinguishable from zero. Its velocity relative to the cluster is minus 170 kilometers per second, plus or minus 107, which again is consistent with not moving relative to the cluster at all. And when the Chandra X-ray Observatory located the peak of the hot gas emission, the brightest point of that 90 million degree cloud, the galaxy was found sitting 0.42 kiloparsecs from it, 1,400 light-years in a system 12 million light-years across. It is not a galaxy inside a cluster, it is the thing the cluster is arranged around, the bottom of the well. And in October of 1990, 3 astronomers pointed a camera at that well, measured the faint light pooling in it, and produced a number that has been repeated ever since, by textbooks, by documentaries, by every list of the largest things in the universe. That number was wrong, and the reason it was wrong is not carelessness. It is much more interesting than that. Part 4. The Number That Escaped. On the 26th of October, 1990, the journal Science published a short paper by 3 astronomers, Juan Uson, Stephen Bown and Geoffrey Kuhn, under the title The Central Galaxy in Abell 2029, an Old Supergiant. A longer and much more detailed version appeared the following year in the Astrophysical Journal. What they had done was straightforward in concept and very difficult in practice. They had imaged the cluster in red light and gone looking for the diffuse glow around the central galaxy, the faint outer light that ordinary photographs simply lose in the background, and they found it, extending much further than anybody had previously traced. Here is their actual result, in their actual language, because the precision matters. They detected an elliptical component of diffuse light, an extended halo of the central galaxy, with a constant eccentricity of 0.9, following a Defies profile out to a distance of 425 H-inverse kiloparsecs. The integrated luminosity of the galaxy with this halo, they wrote, was 5 times 10 to the 11th H-inverse squared solar luminosities, and in their conclusion they said, "This is possibly one of the largest and most luminous galaxies in the universe." 2 of those terms deserve unpacking, because they will keep reappearing. A Defies profile is a specific mathematical curve worked out by Gérard de Vaucouleurs in 1948 that describes how the brightness of an elliptical galaxy falls off with distance from its centre. It is sometimes called the r to the 1/4 law, and it fits ordinary ellipticals startlingly well. Its defining characteristic for our purposes is that it has no end. The curve declines forever. Mathematically, a de Vaucouleurs profile never reaches 0. So the moment you describe a galaxy with 1, you have committed yourself to an object that formally has no edge, and any size you quote afterward is a place you chose to truncate a curve that did not want to be truncated. The eccentricity of 0.9, meanwhile, means the glow was strongly flattened. Not a sphere, but something closer to a lens. That will matter too. And the title of the science paper is doing real work as well. An old supergiant. They were not only saying it was large, they were saying it was finished. The colours of the light told them the stars in it were ancient and that no new ones were being made. Whatever this thing was, it had done its growing a long time ago. That, as it happens, is a conclusion that the 2026 paper is going to contradict rather spectacularly. Now, notice the letter H in those numbers. That little symbol is going to do an enormous amount of damage. The letter H is a placeholder. It stands for the Hubble constant, the number that describes how fast the universe is expanding, divided by 100 kilometers per second per megaparsec. Astronomers use it because distances in cosmology all depend on that expansion rate, and in 1990 nobody knew what the expansion rate was. There was an actual, occasionally bitter, decades-long argument about it. One camp, led by Alan Sandage, put the Hubble constant at around 50. Another camp, led by Gérard de Vaucouleurs, put it at around 100. That is a factor of 2, and it propagates into a factor of 2 in every distance and every physical size you calculate. So rather than pick a side, astronomers wrote their results with an H in them and let the reader plug in whatever value they believed. In 1990, the working convention in most of the literature was H equals 0.5, a Hubble constant of 50. So, take the measurement, 425 H-inverse kiloparsecs, divide by 0.5, you get 850 kiloparsecs. That is a radius. Double it for a diameter, and you get 1,700 kiloparsecs, which is 5.5 million light-years, and the science paper had gone slightly further, saying the halo could be traced to more than a megaparsec, which doubled is around 6.5 million light-years. The New York Times ran the story on the day of publication, under a headline about the sighting of the largest galaxy hinting at clues on the clustering of matter. The figure they printed was 6 million light-years, and they noted that this was more than 4 times the diameter of the previous record holder. That is the origin. That is where the number comes from. Every list of the largest galaxies in the universe, every documentary graphic, every classroom poster that has told you IC1101 is around 6 million light-years across. All of it descends from one radius, doubled, under a value for the expansion rate of the universe that astronomers abandoned a long time ago. Because we now know what the Hubble constant is, at least to within a few percent, it is around 70, which makes H equal to 0.7, which turns 425 H-inverse kiloparsecs into 607 kiloparsecs of radius, and about 4 million light-years of diameter. So a third of the famous number was never a property of the galaxy at all. It was a property of a constant that got revised. But that is the smaller of the two problems, and honestly it is the boring one. The bigger problem is sitting right there in the 1991 paper, written by the authors themselves, in a sentence that almost nobody has ever quoted. Here is what they wrote. Whether this diffuse light is called the CD envelope or diffuse intergalactic light is a matter of semantics. It is a diffuse component which is distributed with elliptical symmetry about the centre of the cluster potential. Read that again, because it is one of the most honest sentences in the literature on this object. They are saying, we measured a glow. We do not know whether this glow belongs to the galaxy or to the cluster. Those two possibilities look identical in our data, and the fact that the glow is arranged around the center of the cluster's gravity, rather than around the galaxy specifically, is a hint that it might be the clusters. They did not claim it was the galaxy. They declined to claim it. In print. In the paper. And then the number went around the world and the sentence did not. There is something quietly bleak about that, and I do not think it reflects badly on anybody involved. Nobody lied. The measurement was good. The caveat was published. It simply did not survive contact with a press release, because a caveat is not a fact-shaped thing and a number is. 6 million light-years travels. A matter of semantics does not. It took 24 years for anyone institutional to push back publicly. In 2014, the National Radio Astronomy Observatory's public question and answer page took the question directly: what is the size of the giant galaxy IC 1101? And the answer from an astronomer on staff was that he had not been able to find any references to actual measurements of this galaxy, which confirmed the claimed sizes in the 6 million light-year range. Not that the claim was wrong, that there was no measurement behind it, and that is the thing I want you to carry into the rest of tonight, because it is going to come back. A number in a headline is a fossil. It preserves the assumptions that were current on the day it was made, the value of the Hubble constant, the definition of a galaxy's boundary, the state of the argument, and then those assumptions quietly rot away underneath it, while the number itself stays perfectly intact and perfectly quotable. The number does not know that its foundations have been replaced. It just keeps being repeated. There is one more figure from that same 1991 paper that is worth having in your pocket because it foreshadows the whole problem. In the outer annulus they measured, the diffuse light was about 10% of the total light in that region, and when they added everything up, they concluded that the central galaxy plus its envelope emits around 23% of all the light in the entire cluster. Nearly a quarter of the light of a system containing 1,200 galaxies is coming from one object and the glow around it, which raises the obvious question, and it is the question the rest of this video exists to answer. If you cannot tell from the light where the galaxy stops and the glow begins, then what kind of object are you actually looking at? What is this thing? Because it is not a galaxy in the way that the Milky Way is a galaxy. It is something else, built a different way, and understanding how it was built turns out to be the key to understanding why nobody could measure it. Part 5. What kind of thing this is. In 1964, 3 astronomers, Thomas Matthews, William Morgan and Martin Schmidt, published a paper about galaxies that had been identified with radio sources, and buried in it was a piece of classification that has outlived almost everything else in the paper. They noticed that certain galaxies had a particular structure, an elliptical-looking nucleus surrounded by an extensive faint envelope. They called these D galaxies, where D originally stood for diffuse. And then they noticed that some of these, specifically the ones sitting near the centers of rich clusters, were absurd. Their diameters, Morgan and his colleagues wrote, were 3 to 4 times as great as the ordinary lenticular galaxies in the same cluster. So they needed a way to mark those out. They borrowed a letter from stellar spectroscopy. When astronomers classify stars, a lowercase c in front of the spectral type marks a supergiant, a star that has swollen to enormous size. So they took that C and put it in front of the DCD, supergiant diffuse. That is the class IC 1101 belongs to, and it is a class that exists for exactly one reason. Because when a cluster of galaxies has been sitting there for 10 billion years, something happens at the bottom of the gravitational well, and the thing that happens produces objects that do not fit anywhere else on the classification chart. Here is what happens. A brightest cluster galaxy is not born large. That is the single most important thing to understand about IC 1101, and it is the thing that quietly explains every strange fact about it that we are going to encounter. It did not form as a giant. It was assembled out of other galaxies, one at a time, over roughly 10 billion years. Think about the geometry of a cluster. You have a deep gravitational well and hundreds or thousands of galaxies moving around inside it on their own orbits. Those orbits are not stable forever. A galaxy moving through a cluster is moving through a medium, the hot gas, the other galaxies, the dark matter, and it experiences drag. Astronomers call it dynamical friction. As a galaxy moves, it gravitationally pulls the material behind it into a slight overdensity, a wake, and that wake pulls back on it. And over time, the galaxy loses orbital energy and spirals inward. Everything sinks, and the deepest point of the well is the place where everything that sinks ends up. So over 10 billion years, the object at the center of the cluster eats. It eats the galaxies that spiral in, it eats their stars, it eats their dark matter. And the simulations that follow this process in detail suggest that as much as 70% of the stellar mass of a brightest cluster galaxy was not born there. 7 out of every 10 stars in IC 1101 formed somewhere else, in some other galaxy, and were carried into this one by a collision. But, and this is where it becomes strange, the collisions are dry. That word is technical, and it is worth explaining properly, because the difference between a wet merger and a dry merger is the difference between a birth and a funeral. A wet merger is what happens when two spiral galaxies collide while they still have their gas. Spirals are full of cold hydrogen, and when two of them hit each other, those gas clouds slam together, get compressed, and collapse. The result is a starburst, an enormous, violent, brilliant episode of star formation, millions of new stars igniting at once, the galaxy blazing blue and bright for a few 100 million years. It is the most spectacular thing that happens to galaxies. Our own Milky Way will do this in about 4.5 billion years when Andromeda arrives. A dry merger has none of that. In a dry merger, both galaxies have already used up or lost their cold gas. There is nothing left to compress. So when they collide, nothing ignites. Nothing new is made. What happens instead is almost eerily quiet. The two galaxies pass into each other, and the stars do not collide. They essentially never do. This is one of those facts that sounds like a mistake the first time you hear it. Two galaxies containing hundreds of billions of stars each pass directly through one another, and, in all likelihood, not one single star physically strikes another. The reason is spacing. If you shrank the Sun to the size of a grain of sand, the nearest other grain of sand would be about 6 kilometers away. That is the emptiness of a galaxy. Two clouds of sand grains 6 kilometers apart can be poured through each other all day without a single collision. So what actually changes in a dry merger is not the stars, it is their orbits. The gravitational chaos of the encounter scrambles every trajectory in both galaxies. Whatever ordered rotation existed, whatever disks, whatever spiral arms, gets destroyed, and what emerges is a swarm. Stars on randomly oriented orbits going in every direction, held together by their collective gravity, with no plane and no preferred direction, and no rotation to speak of. That is what an elliptical galaxy is. It is not a shape that formed, it is a shape left behind, and IC 1101 is what you get when you do that dozens of times. If you want something to picture, you already have one. In April of 2019, the Event Horizon Telescope released the first image ever taken of a black hole's shadow, and the galaxy it was pointed at was M87, the giant elliptical at the center of the Virgo cluster, about 55 million light-years away. M87 is exactly this kind of object. Same class, same origin story. A featureless, rotation-poor, gas-starved ellipsoid squatting at the bottom of a cluster's gravity, surrounded by an enormous faint envelope, having spent 10 billion years absorbing its neighbours. If you have seen that orange ring, you have seen the family portrait. IC 1101 is M87 scaled up. Bigger cluster, longer meal, larger everything. And the reason that scaling matters is that these objects are not static. This is the point I want to plant now and come back to at the very end of tonight, so hold on to the phrase, a galaxy like this is not finished. It is not a thing that formed and then sat there. It is a process that is still running, and the picture we have of it is a frame pulled out of a film that has been playing for 10 billion years and has not stopped. You can see the fingerprints of it directly. When astronomers measured how fast the stars are moving in the center of IC 1101, they found a rotation velocity of essentially 0 out to 13 kiloparsecs from the middle. 0. In our galaxy, the Sun is travelling around the center at about 230 kilometers per second, in an orderly, flat, rotating disk. In the center of IC 1101, nothing is going around anything. The stars are just moving, at hundreds of kilometers per second, in whatever direction the last collision left them pointing. The galaxy's official classification, incidentally, is still disputed, and the dispute is a symptom of the same problem. Some databases list it as an elliptical. The third reference catalogue calls it a lenticular. Alan Dressler, who studied its dynamics in 1979, treated it as a CD. The confusion comes from two real structural oddities. The outer halo is twisted about 20 degrees out of alignment with the inner body, and the contours of equal brightness go distinctly boxy beyond about 20 arcseconds from the centre. Those features could suggest a disk, but the detailed structural work rules a disk out. There is no rotation, and boxy contours are a signature of a system built by mergers, not by settling. The twist, though, keep the twist. A halo that is rotated 20 degrees relative to the galaxy it supposedly belongs to is not a small detail. It is a hint that the halo may not belong to the galaxy at all. And the last thing to say about this object before we move outward is that it is finished with the business of making stars. There is no emission from the nucleus in visible light. There are no signs of recent star formation anywhere in it. There is no dust in the core. Astronomers have an unsentimental phrase for galaxies in this condition, and the phrase is red and dead. Every star in IC 1101 that is ever going to exist already exists. The whole system is coasting, slowly reddening as its brightest and bluest stars burn out one after another, with nothing arriving to replace them. Which means every gram of growth this galaxy has left comes from swallowing something else. It cannot make, it can only take. And that fact, that everything this object gains, it gains by eating, turns out to have a consequence that nobody anticipated. Because when you eat a galaxy, you do not get all of it. Some of it spills. Part 6. The Glow Between the Galaxies. In 1951, Fritz Zwicky published a paper about the Coma Cluster in the Publications of the Astronomical Society of the Pacific, and in it he wrote a sentence that opened a field. One of the most interesting discoveries made in the course of this investigation, he wrote, is the observation of an extended mass of luminous intergalactic matter of very low surface brightness. Zwicky was looking at the space between the galaxies in Coma, and he was seeing a glow there. Not galaxies, not stars he could resolve. A faint, smooth, continuous light filling the gaps, and he suspected, correctly as it turned out, that it was made of stars that were not inside any galaxy at all. It took the field about 70 years to fully catch up with him. Deep observations of cluster after cluster have now confirmed that first visual impression. The space between galaxies in a cluster is not empty, and it is not dark. It glows. Astronomers call it intracluster light, and it is the most underappreciated component of the visible universe. Here is what it is. When a galaxy falls into a cluster, it does not survive intact. Tides pull at it. The gravitational field of the cluster is not uniform. It is stronger on the side nearer the centre, and that difference stretches the infalling galaxy and strips stars off its outer regions. Those stars do not fall into the central galaxy. They do not stay with their parent galaxy either. They end up on wide, slow, independent orbits around the cluster as a whole. They belong to nothing. Do that thousands of times, over 10 billion years, and you accumulate an enormous population of stars that are, in the most literal sense, homeless. Current estimates put the intracluster light at somewhere between 10 and 40% of all the starlight in a cluster. Somewhere between a tenth and nearly half of the stars in a galaxy cluster are not in a galaxy. The best evidence on where those stars come from is worth pausing on, because the intuitive answer is wrong. You would guess that intracluster light comes from small galaxies being ripped apart, the dwarfs, the weaklings, the ones with the least gravity to hold themselves together. But when astronomers work out the colours and the chemistry of intracluster stars, they point at something else. The progenitors appear to be galaxies of around 5 times 10 to the 10th solar masses, which is to say, galaxies about the size of the Milky Way. That is not a comfortable thought, and it should not be. The glow between the galaxies is mostly made of the outer layers of galaxies like ours. It is not built from the destruction of the small and the fragile. It is built by shaving the edges off the large. There is also a cross-check that rules the dwarf explanation out arithmetically. If you tried to make all of that light by destroying dwarf galaxies, you would need so many of them that the cluster's population of surviving galaxies would look completely different from what we observe. The books do not balance. It has to be the big ones, losing their outskirts a little at a time, and a substantial fraction of it, up to about 30% in simulations, was not even stripped in the cluster. It was stripped earlier, while the galaxies were still in smaller groups before those groups ever fell in. Nearly half of all galaxies and clusters arrived not as individuals but as members of a group. They were already partly disassembled when they got there. Now, bring this back to IC 1101, because this is the moment where the whole problem of measuring the thing finally becomes visible. In 1979, Alan Dressler measured how fast the stars in ICL-N01 are moving as a function of distance from its centre. What he found is one of the strangest velocity profiles in the literature, and it is the hinge of everything tonight. Within about 5 kiloparsecs of the centre, the stars have a velocity dispersion of around 375 kilometers per second. Between 6 and 62 kiloparsecs out, it rises to about 425, plus or minus 25, and beyond 62 kiloparsecs, it goes above 500 kilometers per second. The stars are getting faster as you go outward, that is backwards. In a normal galaxy, gravity is strongest near the middle, so the stars near the middle move fastest, and as you go out and there is less mass pulling on you, they slow down. Our own galaxy does something roughly like that, with a famous flat region in the middle that is one of the main pieces of evidence for dark matter. But a rising velocity dispersion, climbing steadily as you move away from the centre, that means something else is pulling, and it is obvious what. Remember the number from earlier, the velocity dispersion of Abell 2029, the entire cluster is 967 kilometers per second. As you walk outward through ICL-N01, the stars are climbing from the galaxy's number toward the cluster's number. They are transitioning gradually and without any discontinuity, from being held by the galaxy to being held by the cluster. That is what the astronomers who did the structural work concluded, in exactly those terms. The rise is caused by the growing contribution of halo stars, which trace the cluster potential rather than the galaxies. So let me put you inside it, because I think this is worth feeling rather than just knowing. Imagine standing at the centre of ICL-N01 and walking outward. Not that you could, but imagine it. Around you at the start, stars are moving at 375 kilometers per second in every direction at once, not orbiting in a plane the way the sun does, but swarming, like a cloud of insects with no preferred direction and no rotation at all. Walk outward, 5 kiloparsecs, 20. The stars are thinning out around you and they are speeding up. 425 kilometers per second. 60 kiloparsecs from the centre, and now they are going faster than 500. Keep walking. At some point, and this is the part that has no signpost, you're standing among stars that are not being held by the galaxy underneath you anymore. They are being held by a cluster containing 1,200 galaxies and a quadrillion solar masses of dark matter, and the galaxy is now just the brightest thing in the neighbourhood rather than the thing you're inside. There was no wall, there was no gate, nothing announced the crossing, nobody rang a bell, the stars around you did not change colour or thin out abruptly. All that happened is that somewhere in that walk, imperceptibly, the answer to the question, what is holding this star, changed from one thing to another. And you have exactly the same problem at home, incidentally, just less dramatically. There is no signpost at the edge of the Milky Way either. The sun is not sitting inside a bounded object with a rim. It is sitting inside a density gradient that thins out until it becomes something else. The two other signatures the astronomers look for both show up here too. The outer light of ICL-N01 gets more flattened as you go out. The ellipticity increases with radius, and the halo is rotated 20 degrees relative to the inner galaxy. Both of those are exactly what you expect if the outer glow is a genuinely separate component that is shaped by the cluster rather than by the galaxy. Which brings us to a genuine scandal, and I use that word deliberately, because astronomers have been trying to measure how much intracluster light there is in various clusters, and the answers they get depend catastrophically on which method they use. Take one cluster, Abell S263. Measure its intracluster light with a wavelet-based technique, and you get 23%. Measure the same cluster with the same data, using a surface brightness cut, and you get 3.2%, a factor of 7, same cluster, same photons. It is not an isolated case. Abell 85 gives 6.5% one way and 11% another. Across a sample of 170 clusters measured with 4 different methods, the scatter runs from 34 to 71%. Mireia Montes, one of the authors of the 2026 paper we started with, wrote a review of this field a few years ago, and her verdict on the situation was blunt. Without a fixed definition, she wrote, any conclusion will be meaningless. And her suggested solution was genuinely radical. Given that most of a central galaxy's stellar mass was accreted anyway, maybe it does not make sense to separate the two components at all. Maybe you should just treat the galaxy and the glow as one thing and stop pretending there is a boundary. There is a beautiful footnote to all this, and it deserves saying because it is the redemption of the whole messy business. This faint, ambiguous, hard-to-measure glow turns out to be the single best optical tracer of dark matter that anybody has found. When you compare maps of intracluster light with maps of where the dark matter actually is, derived independently from gravitational lensing, the two agree to within about 25 kiloparsecs out to 140 kiloparsecs from the center. The faintest thing you can see in a cluster is the most accurate picture available of the thing you cannot see at all. But that does not help with our problem, because if you cannot separate the galaxy from the glow by eye, and you cannot separate it by brightness, and 4 different methods disagree by a factor of 7, then how could anyone ever say how large this galaxy is? The answer is that they could not. Not with any tool that existed. Somebody was going to have to build a new one. Part 7. The ruler that had to be invented. Let us stop for a moment and put the pieces on the table together, because we are about halfway through and the shape of the problem has changed since we started. We have an object that was discovered by accident in 1890 by a teenager who could not agree with his father about what it looked like, and which entered the permanent scientific record as a blank space in a list. We have a cluster around it, catalogued in the 1950s by a graduate student with a magnifying glass, containing 1,200 galaxies and a quadrillion solar masses and a cloud of 90 million degree gas that outweighs every star in it. We have a famous number, 6 million light-years, that turns out to be a radius, doubled, using a value for the expansion of the universe that nobody has believed since the 1990s, applied to a glow that the people who measured it explicitly refused to say belonged to the galaxy. And we have a galaxy whose outer stars are demonstrably, measurably, being held by something other than the galaxy. So the question we started with is still unanswered, and now we can see why it is hard. Where does the galaxy end and where does the cluster begin? There is no feature to point at. There is no gap. The stars in the middle and the stars in the halo are the same kind of star mixed together, shading into one another with no break. The transition is real, the velocity dispersion proves it, but it is gradual, and it happens over hundreds of thousands of light-years. And here is the thing that took me a while to properly appreciate. The reason nobody could answer this question is not that nobody had a big enough telescope, it is that nobody had a ruler. I want to walk you through the rulers, because it is genuinely one of the more satisfying things in observational astronomy, and because by the end of it, you will understand something that most people who quote galaxy sizes do not. That essentially every size ever published for any galaxy is a convention with no physical meaning whatsoever. Ruler 1 is the effective radius, also called the half-light radius. The definition is simple. Add up all the light of the galaxy, then find the radius of the circle that contains exactly half of it. That is your size. It sounds robust, and it is not. And IC 1101 breaks it in the most spectacular way available, because the definition depends entirely on what you decide the total is. Include the outer halo and the half-light radius balloons. Leave it out, and it collapses. One published attempt to fit a single mathematical curve to IC 1101's brightness profile produced an effective radius of 439 kiloparsecs. Another study, working from blue photographic plates, got 65 kiloparsecs, plus or minus 12, 65 and 439, a factor of 7 for the same object, from the same kind of measurement, and neither number is fraudulent. They are both what you get when you force one smooth curve onto a profile that is actually made of at least 4 distinct pieces, and the answer depends on which piece your data happen to emphasize. It is like trying to measure the outskirts of a city through a lens ground for looking at its town hall. Ruler 2 is the isofotal diameter, which usually goes by the shorthand D25. An isophote is a contour of equal brightness, like a contour line on a map but for light instead of altitude. The convention, which dates back to the 1930s, is to draw the contour where the surface brightness of the galaxy falls to 25 magnitudes per square arc second in blue light, and call the diameter of that contour the size of the galaxy. This is at least reproducible, but look at what it actually depends on. It depends on which filter you use, because galaxies have different sizes in different colours. It depends on the stellar population, because an old red galaxy and a young blue one of identical physical extent will give different contours. It depends on dust, and fatally, it depends on distance. Not because faraway galaxies look smaller, every measure has that problem and it is easily corrected, but because of something called cosmological surface brightness dimming. As the universe expands, the light from a distant extended object is dimmed by a factor of 1 plus the redshift, raised to the 4th power. That is not an instrumental effect. It is geometry and expansion, and it cannot be undone. At the redshift of Abell 2029, that factor is about 1.35, not huge, but move the same galaxy out to a redshift of 1, and the factor is 16. The identical object, unchanged in every physical respect, would be measured as dramatically smaller, because the contour line you're using would fall much further in. By this ruler, galaxies genuinely shrink as you move them away from you, which is a very strange property for a ruler to have. For the record, IC 1101's isofocal diameter comes in somewhere between about 403,000 and 553,000 light-years, depending on which catalogue you ask and which band they used. Keep those numbers, they're going to look very small in a few minutes. Ruler 3 is the Petrosian radius, which is cleverer. Instead of a fixed brightness, you define the radius where the local brightness drops to a fixed fraction of the average brightness inside that radius. Because it is a ratio, the cosmological dimming cancels out, which is why large surveys use it for their photometry. It is a genuinely better tool. It is still, however, a convention about light, with no physical event happening at the boundary. Nothing changes at the Petrosian radius. It is just a place the arithmetic points to. So all 3 rulers have the same disease. They are all measuring light, and light is not the thing you want. Light tells you where the galaxy is bright. It does not tell you where the galaxy is. And then, in 2020, Ignacio Trujillo, Nushkia Chamba, and Johann Napen published something different. Their proposal was to stop measuring light and start measuring mass, specifically the surface density of stellar mass, in solar masses per square parsec, and then to define a galaxy's size as the radius at which that density drops to 1 solar mass per square parsec. Now, on the face of it, that just looks like swapping one arbitrary threshold for another. Why 1? Why not 2? Or a half? Because 1 solar mass per square parsec is not arbitrary. It is, roughly, the surface density at which gas stops being able to make stars. That is the whole idea, and it is lovely. Star formation is not a smooth function of gas density. Below a certain threshold, a gas cloud cannot overcome its own internal pressure and turbulence, cannot collapse, and simply sits there indefinitely without forming anything. Above it, it collapses and stars appear. This threshold shows up in the observed relationship between gas density and star formation rate across enormous ranges of galaxy type. And when you translate that gas threshold into the stellar mass density it leaves behind, you get something close to 1 solar mass per square parsec. So this contour is not a place we chose. It is a place the physics chose. It is the outer limit of everywhere the galaxy was ever able to build anything. Beyond it, there was never enough material for a star to happen. That is not a convention. That is a wall, the only wall a galaxy actually has. And here is the evidence that it is real, and it is the kind of evidence that should make you sit up. There is a well-known relationship in astronomy between how massive a galaxy is and how large it is. Bigger galaxies are bigger, obviously. But measured with the effective radius, that relationship is loose and messy, with a lot of scatter, and it behaves differently for different types of galaxy. Measured with this new radius, across 5 orders of magnitude in stellar mass, from 10 million solar masses up to 1 trillion, from tiny dwarfs to giants, the relationship collapses into a line with an intrinsic scatter of about 0.06 dex, 3 times tighter than with the effective radius. Think about what that means. You change nothing about the galaxies. You change nothing about the data. You change only your definition of the word size. And 100,000-fold range of objects suddenly falls onto one clean relation. That does not happen when you have picked a better convention. That happens when you have accidentally started measuring something that is actually there. 2 years later, in 2022, Chamba, Trujillo and Napen refined it further. Rather than always using the same threshold value, they looked for the observed drop in the stellar mass density profile itself, the place where the curve turns down, and called that the edge. The value at which the drop happens is not universal. It runs from about 0.6 solar masses per square parsec in dwarf galaxies up to around 3 in ellipticals, and for early-type galaxies that have been rearranged by mergers it may be higher still. That quantity has a name. It is called R-edge, and it is the quantity the 2026 paper reports. So here we are. Remember what those astronomers wrote in 1991. when they could not decide whether the glow around this galaxy belonged to it or to the cluster. They said it was a matter of semantics. They were right. And they were also, in a way they could not have known, describing the discovery. Because the semantic problem was a physical problem wearing a disguise. The reason nobody could say where the galaxy ended is that the word end had never been given a physical referent. Solve the semantics. Find the one boundary that corresponds to a real event rather than a chosen brightness, and the measurement becomes possible. The ruler now exists. It has been tested on dwarfs and on spirals and on ordinary ellipticals, and it works. It had never been pointed at the biggest thing in the sky, partly because nobody had got around to it, and mostly because, to use it on an object like this, you would need images of a depth that nobody had ever taken. Part 8. 2.5 meters. On a volcano. There is a ridge on the island of La Palma, in the Canaries, at about 2,400 meters above sea level, called the Roque de los Muchachos. It is the rim of an ancient volcanic caldera, and for most of the year it sits above the layer of cloud that forms over the Atlantic, so that from up there the weather is happening somewhere below you. It is one of the best observing sites on the planet, and it is crowded with telescopes. One of them is the Isaac Newton telescope, and I want to be honest about what it is because the honesty is the interesting part. It is a 2.5 meter reflector. It was built in the 1960s and first went into service in 1967, in Sussex in England, where the weather is not good for astronomy, and where it spent about 15 years being a slightly disappointing instrument before somebody sensibly decided to take it apart and ship it to a volcano. It has been on La Palma since the 1980s. 2.5 meters is not a large telescope by modern standards. The Hubble Space Telescope's mirror is 2.4 meters and it is in space. The James Webb Space Telescope is 6.5. The extremely large telescope currently being built in Chile will be 39. There are wealthy amateurs with instruments approaching a meter. The Isaac Newton telescope is, in the world of professional astronomy, a workhorse of unremarkable size and considerable age. And it just measured the largest galaxy anybody has ever measured. This was not one by aperture. I want to make that completely clear, because the instinct, mine too, is to assume that a record-breaking observation must have come from a record-breaking machine. It did not. It came from exposure time, from a well-understood optical system, and above all from the removal of error. The camera used is the wide-field camera, a mosaic of 4 detectors covering roughly a third of a square degree of sky, a patch about as wide as the full moon on a side. What matters here is not sharpness. It is that you can capture a large, flat, well-characterized area in one go, because the thing you are fighting is spread across the whole frame. They observed in 2 filters, G and R, the green and the red of the standard photometric system. 2, not 1, and not for prettiness. The difference between the 2, the color, is one of the 3 independent indicators they would use to find the edge. You need at least 2 bands to have a color at all, and the depth they reached is the number that makes this whole thing work. 30 magnitudes per square arc second. Let me unpack that slowly, because it is the most important technical figure in this story, and it is expressed in units designed by 19th century astronomers to be as unintuitive as possible. Surface brightness is how much light is coming from each little patch of sky, and it is measured in magnitudes. The magnitude scale is backwards. Bigger numbers mean fainter, and it is logarithmic, so that every 5 magnitudes is a factor of exactly 100 in brightness. A dark night sky, on a moonless night, at high altitude far from any city, glows at roughly 22 magnitudes per square arc second. And I want to stress that this glow is not a failure of the sight. It is the sky itself. It is air glow, oxygen and hydroxyl molecules in the upper atmosphere quietly emitting light about 90 kilometers above your head. It is starlight from our own galaxy, scattered. It is zodiacal light, sunlight bouncing off dust in the plane of our solar system. Even in perfect conditions, in the middle of nowhere, the sky is not black. It is very faintly grey, and it always has been. The Sloan Digital Sky Survey, the survey that underpins an enormous fraction of everything we know about galaxies statistically, reaches about 26.5 magnitudes per square arc second. This observation reaches 30. Do the arithmetic with me. From 26.5 to 30 is 3.5 magnitudes, which is a factor of about 25 to 40 in brightness depending on how you round it. So this is roughly 40 times deeper than the standard survey data that most galaxy science is built on. But the number that should actually stop you is the other one. From 22 to 30 is 8 magnitudes. 8 magnitudes is a factor of about 1600. The structures being measured here are more than 1,000 times fainter than the darkest natural sky on Earth. There is a piece of fine print attached to that number, and it is worth including because it tells you what kind of detection this is. The depth is quoted at 3 sigma in an area equivalent to 10 arcseconds by 10 arcseconds, which means this is not a measurement of individual points of light. Nobody is resolving stars out there. What is being detected is a statistical excess, a very slight surplus of photons, averaged over a patch of sky 100 square arcseconds in size, standing 3 standard deviations above the noise. You could not point at any one pixel and say there is a galaxy in it. You can only say that across this patch, taken together, there is more light than there should be, and the odds of that being a fluctuation are small. That also tells you why nobody had done this before. Reaching this depth is not a matter of one long exposure. Random noise falls only as the square root of the time, so going 4 magnitudes deeper than a standard survey costs you something on the order of 1,000 times the exposure. But the systematic errors, the scattered light, the flat field, the sky gradients, do not fall at all, no matter how long you stare. They just sit there, unchanged, waiting. Which means the extra time is necessary and completely insufficient. You also have to understand your instrument well enough to subtract everything it is doing to your image. Reframe what that means because it inverts the whole picture of what observing is. You're not looking for a faint light against a dark background. There is no dark background. You're looking for a very slight irregularity in a glow that is already 1,600 times brighter than the thing you want to detect. The signal is not competing with darkness. It is buried under something enormously brighter, and every single source of stray light in the entire system matters more than your target does. Which means the limiting factor is not the sky, and it is certainly not the size of the mirror. The limiting factor is the telescope itself. Here is the problem, and it is beautiful in a horrible way. No optical system focuses a point of light to a point. Not one. Not the finest lens ever ground. Not a perfect mirror. Not anything. What you get instead is a bright core surrounded by a halo of scattered light, some of it from diffraction, some from imperfections in the optics, some from dust on the surfaces, some from light bouncing between elements. Astronomers call the whole shape the point spread function. For ordinary work, you only care about the core, because that is where essentially all the light is. But essentially all is not all. Out in the wings of that shape, at levels thousands and tens of thousands of times fainter than the core, the light keeps going. It extends out for arc minutes, it is invisible in any normal image, and it is comfortably brighter than 30 magnitudes per square arc second. So consider what happens when there is a bright star in the same part of the sky as your target. That star is not a local problem confined to a few pixels. Its scattered light is smeared across a large fraction of your image at exactly the brightness level you're trying to measure. If you do not remove it, you will measure it, and you will call it galaxy. And there are a lot of stars in the way, not the galaxy's stars, our stars. Foreground stars in the Milky Way, a few hundred or a few thousand light years away, sitting in the line of sight to an object a billion light years behind them, throwing their light across it. It is light pollution, but it is not coming from a city. It is coming from our own galaxy, and there is no way to switch it off. There are other enemies too, and they are all of the same kind. The flat field, the map of how sensitive each pixel is, needs to be known to well under 1%, because a 1% error is completely invisible in normal imaging and utterly catastrophic here. It manufactures a slow gradient across the frame that looks exactly like the faint halo of a giant galaxy. The gaps between the 4 detectors have to be dithered over, so no part of the target sits permanently in a crack. Bad columns have to be averaged out. Every one of these is a systematic error rather than a random one, which means that no amount of extra exposure time will make it go away. So before this team could measure the largest galaxy in the sky, they had to remove the sky. Then they had to remove the telescope. And then, strangest of all, they had to remove the galaxy. Part 9. Subtracting. The sky, star by star. Watch what they do. The images are stacked. The frame contains the galaxy, and it contains hundreds of foreground stars and it contains a faint grey wash of scattered light that belongs to none of them. The first job is to learn the telescope, not to model it approximately, to characterize in detail exactly how this specific instrument spreads a single point of light across its field. This is done with the stars in the images themselves. The very bright ones are useless in the middle because their cores are saturated, blown out to blank white, but they are perfect for the far wings, where their scattered light is still measurable arc-minutes away. The fainter ones are useless in the wings, because out there their light has dropped below the noise, but their cores are clean and unsaturated. So you take the bright stars for the outside and the faint stars for the inside, and you stitch them together into one continuous profile that spans an enormous range of brightness, from the blazing centre down to the faintest measurable trace, degrees of magnitude below it. That composite shape is the extended point spread function. It is a map of everything the telescope does to a point of light. And building one is a peculiar kind of labour. It is not observing in any romantic sense. Nobody is at an eyepiece. Nobody is on a mountain in the cold. It is somebody at a screen, at sea level, months after the photons arrived, going through a stacked image and asking of every bright thing in it, how much of what surrounds you is you, and how much is real. It is closer to restoration work than to exploration. The kind of thing a conservator does to a painting, lifting off a century of yellowed varnish a square centimetre at a time, in the hope that there is something underneath, and that they have not damaged it getting there. The difference is that a conservator knows a painting is under the varnish. Here, nobody knew whether there was anything at all. It was entirely possible that after all this work the answer would be, the galaxy just keeps going, there is no edge, the profile declines forever, and we have spent a year proving that a question was unanswerable. Then the subtraction begins. They go through the frame and they find more than 250 foreground stars. Each one gets measured, each one gets its own scaled copy of the point spread function, and each one gets removed. One at a time. 250 separate acts of erasure, each of them deleting the faint skirt of light that one star in our own galaxy has been throwing across an object 1 billion light-years away. Think about the geometry of that for a second. Each of those stars is in the Milky Way, a few hundred or a few thousand light-years from here. Their light is, in cosmic terms, brand new. It left them within recorded human history, some of it within a single lifetime, and it is sitting in front of a light that is 1 billion years old, hiding it. The nearest, youngest photons in the frame are the ones drowning out the oldest, most distant ones. The team is not removing noise. They are removing our own neighbourhood, and then they do the same thing to the galaxy. This is the step that sounds like a mistake and is not. A bright extended object also scatters its own light through the optics. The dense luminous centre of ICL-101 throws light outward through the telescope in exactly the same way a star does, and that scattered light lands in the outskirts, in precisely the region where you're trying to detect a real, physical, extremely faint halo. If you do not model and remove it, the galaxy manufactures a fake halo out of its own centre, and you measure that and announce a discovery. Some fraction of every claimed giant halo in the history of this field has been exactly that, a bright galaxy, smeared by its own telescope. So the centre gets subtracted too, and what remains in the outskirts is only what the optics cannot account for. On top of all of that, they apply a hybrid wavelet-based deconvolution. Wavelets are a mathematical technique for taking an image apart by physical scale, separating the structures that vary over a few pixels from the structures that vary over thousands of pixels, without ever having to assume in advance what shape any of them should be. That last clause is the important one. Every previous attempt to measure this galaxy involved fitting a curve, a de Vaucouleurs profile, a Cercic profile, a sum of several, and every one of those fits imposed an assumption about what the answer was going to look like before the data was allowed to speak. That is how you get a 439 kiloparsec effective radius. You do not get it from the galaxy, you get it from the curve you insisted on. A wavelet decomposition does not insist. It separates diffuse from compact and lets whatever is there be whatever it is. And here is what I find genuinely lovely about all of this, and it is worth saying plainly, because it inverts the popular image of what discovery looks like. The largest galaxy anybody has ever measured was found by deleting things, not by gathering more light, not by a bigger mirror or a longer stare or a better detector, by systematically identifying every photon in the frame that could be accounted for by something else, by the atmosphere, by the instrument, by our own galaxy's foreground stars, by the target's own scattered core and taking all of it out. The image gets emptier and emptier as the work proceeds. Structures vanish, halos collapse. Things that looked real turn out to have been the telescope all along, and the thing they are looking for is whatever refuses to disappear. What refused to disappear in this case was measured 3 different ways. The first is the surface brightness profile, how bright the galaxy is as a function of distance from its centre. That is the classical measurement, the one everybody has always done. The second is the colour profile, the difference between the G band and the R band, again as a function of radius. Colour tells you about the stellar populations, how old they are, how much heavy element enrichment they carry. A change in colour means a change in the kind of stars you're looking at, which means a change in where those stars came from. The third is the stellar mass density profile, how many solar masses of stars there are per square parsec at each radius, converted from the brightness using the colour to estimate the mass-to-light ratio. That is the one that matters most, because that is the quantity the new definition of a galaxy's edge is written in. And crucially, this is a detail that turns out to carry the whole result. They did not do this by averaging around the galaxy in circles. They measured the profiles along many different position angles, in different directions from the centre, separately. That is more work and it is much noisier, and there was a very good reason to do it. Averaging around an object assumes the object is symmetric. If it is not, if there are lumps, streams, asymmetric features on one side and not the other, then averaging deliberately destroys exactly the information that makes those features detectable. It smears them into the mean, and they cease to exist. IC 1101, as we're about to find out, is not symmetric, and if this team had done the standard thing and averaged in circles, they would have got a number, and it would have looked fine, and they would have missed the most interesting result in the paper. So, 3 independent diagnostics, measured in many directions, on the deepest images ever taken of a single galaxy, after the sky and the telescope and 250 foreground stars and the galaxy's own glare had all been carefully taken out. Why 3 and not 1? Because any single profile can produce a wiggle by accident. Noise does that. Systematic errors do that. A break in one curve is a suggestion. But if the brightness turns down, and the colour changes, and the mass density drops, all at the same distance from the centre, that is not an artifact. That is an event. All 3 of them changed in the same place. Part 10. 260 kiloparsecs. 260 kiloparsecs. That is where the main body of IC 1101 ends, measured along its long axis. The surface brightness turns down, the colour changes, the stellar mass density drops. All at the same distance from the centre, in multiple independent directions, in the deepest images ever taken of a galaxy. 260 kiloparsecs is about 850,000 light-years. Double it for a diameter, and you get approximately 520 kiloparsecs, about 1.7 million light-years. And inside that boundary, the galaxy contains 3.4 trillion solar masses of stars. I want to be precise about what that figure includes, because the precision is part of the point. 3.4 trillion solar masses of stars, not stars plus gas, not stars plus dark matter, just the stars, the actual luminous thermonuclear objects. The dark matter of this system is a separate and much larger quantity, and the hot gas of the cluster outweighs all the stars in all 1,200 galaxies combined. That trillion-scale number is only the part that shines. Let me put you out there for a moment at the boundary, because I think it deserves more than a number. You're 260 kiloparsecs from the centre of IC 1101, 850,000 light-years out, and there is essentially nothing to see. The nearest star to you is impossibly far away. This is not a place with a night sky in any sense you would recognise. It is a place where the individual stars are so widely spaced that if you were standing on a world here, the sky would be close to empty. Behind you, if you look back, the galaxy is a soft diffuse glow with no visible structure, filling a large part of the sky, offering no detail at all. Ahead of you is the cluster, and there is no line on the ground. Nothing marks this place. The only reason it is a boundary is that the number of solar masses of stars per square parsec has just crossed below a threshold, and beyond it, the gas was never dense enough to make a star. You're standing at the outer wall of everything this galaxy ever built, and you would not be able to tell. Now let us do the comparisons, because the comparisons are where the number stops being abstract. Our galaxy, the Milky Way, is about 100,000 light-years across as a disk. IC 1101 is 1.7 million. That is a factor of 17 in length. Because volume goes as the cube of length, if you treated both as spheres of those diameters, IC 1101 would enclose roughly 5,000 times the volume. By stellar mass, the Milky Way weighs in at something around 5 to 6 times 10 to the 10th solar masses. Call it 60 billion suns worth of stars. IC 1101 has 3.4 trillion. That is somewhere between 55 and 60 Milky Ways in stars alone. Here is the one that I think lands hardest. The distance from the Milky Way to the Andromeda Galaxy, the nearest large galaxy to us, the one that is currently approaching at 110 kilometers per second and will collide with us in about 4.5 billion years, is roughly 2.5 million light-years. IC 1101, edge to edge, is 1.7 million. So if you put IC 1101 where the Milky Way is, its outskirts would extend about 70% of the way to Andromeda. It would fill most of the gap between us and our neighbour, and one more. The local group, our galaxy, Andromeda, the Triangulum Galaxy, and roughly 80 smaller companions, everything gravitationally bound to us, spans about 10 million light-years and contains something on the order of 2 trillion solar masses in total, counting the dark matter, which is most of it. IC 1101 contains more mass in stars alone than our entire local group contains in everything. There is something else about that boundary that I do not want to slide past, because it is easy to hear the word edge and picture the wrong thing. The light does not stop at 260 kiloparsecs. That is not what an edge is here. Go past it, and there are still stars. There are stars for a very long way past it. What changes is the character of them. Inside the boundary, the density of stellar mass declines at one rate. Outside it, it declines at a different, steeper rate, and the colour of the light shifts, and the whole population starts behaving like something that belongs to the cluster rather than to the galaxy. It is a change in regime, not a cliff, and that is precisely what makes it meaningful. A brightness contour is a place where your instrument gives up. This is a place where the physics changes. Inside the edge, you're looking at material that this galaxy assembled and holds. Outside it, you're looking at the glow between the galaxies, the homeless stars, the accumulated debris of 10 billion years of cannibalism, arranged around the cluster's gravity rather than the galaxy's. The two populations were always mixed together in the images. What the new measurement did was find the seam. Now compare this to what the catalogues have been saying. Remember the catalogued angular size of this object, 1.2 arc minutes by 0.6. The edge that was just measured sits about 170 arc seconds from the centre, which is nearly 3 arc minutes of radius, so close to 6 arc minutes across, 5 times the catalogued figure, and its isophytal diameter, the D25 number, comes in at somewhere between 403,000 and 553,000 light-years, depending on the catalogue, between a quarter and a third of the real thing. That gap is not a scandal. It is a measurement of how much light our standard catalogues throw away, because they were built with conventions that stop where the light gets faint rather than where the galaxy gets finished. Every galaxy and every catalogue has a number attached to it that is, in this same way, too small. We have simply never had a reason to care until somebody asked how big the biggest one is. So, where does the galaxy end, and where does the cluster begin? 260 kiloparsecs. There is the answer. After 136 years, somebody finally measured it. But I want to be very careful about what has actually been established, because the honest version is more interesting than the triumphant one. Here is what the paper says, in its own words and with its own hedges intact. The edge radius is among the largest measured for any galaxy to date. It places IC 1101 at the extreme upper end of the mass-size relation, and with a confirmed diameter of around 520 kiloparsecs, IC 1101 stands as the largest galaxy known to date. Known. That word is load-bearing, and it is doing an enormous amount of quiet work, because almost nobody has ever imaged any other candidate galaxy this deep. The reason IC 1101 currently holds the record is not that everything else has been measured and come up short. It is that everything else has not been measured this way at all. There are perhaps half a dozen galaxies in the sky that could plausibly compete, and not one of them has had this treatment. The ultra-deep imaging, the extended point spread function, the 250 subtracted stars, the mass density profile at multiple position angles. Until somebody does that work on the rivals, the record is as much a statement about which object got the attention as about which object is largest. And the rivals are real. ESO 38376, the central galaxy of another cluster, is frequently cited with a major axis diameter of around 1.76 million light-years, very slightly larger than what has just been measured here, and by isophotal diameter it comes in around 453,000 light-years. ESO 306-17, an isolated giant that has already eaten everything comparable in its own group, is usually quoted at about 1.07 million. ESO 444-46 turns up on the same lists. But go and look at where each of those numbers comes from, and you find the problem immediately. They are different quantities. One is a major axis extent from a catalogue. One is an isophotal contour in a particular band. One is a half-light radius scaled up by some factor. They are not measurements of the same thing, and putting them in a ranked list side by side creates an illusion of comparison where none exists. It is like ranking three people by taking one person's height, another person's arm span, and a third person's reach from a seated position, and then announcing a winner. And then there is the category error that dwarfs all the others. You may have seen headlines about a galaxy called Alcyonius, announced in 2022, described as the largest galaxy in the universe at around 5 megaparsecs across, 16 million light-years, or Porphyrion, announced in 2024 at roughly 7 megaparsecs. Those numbers are real. They're also not measuring galaxies. What is 16 million light-years across in Alcyonius is a pair of jets. The black hole at its centre is launching two enormous streams of relativistic plasma out into intergalactic space, and those lobes are what span 5 megaparsecs. The stellar body of Alcyonius, the actual galaxy, the part made of stars, has an isophotal diameter of about 243,000 light-years, which is smaller than IC 1101's by a very comfortable margin. Calling that the largest galaxy in the universe is a bit like measuring a person by how far they can spit. So the record is provisional, and it will probably be challenged, and honestly it should be. But the record is not what this paper achieved. What it achieved is the definition. It demonstrated that the question can be settled at all, that you can take the largest object of its kind and find a real physical boundary in it, and that the number you get means something rather than reflecting a choice of contour. The ranking is temporary, the ruler is not. And then they looked at the middle of the galaxy, which is where things stop making sense. Part 11. The hole at the centre. Before we go any further, I want to flag something, because I think it matters that you know where each piece of this is coming from. What follows is not from the 2026 paper. It is from a different study, published in 2017 in Monthly Notices of the Royal Astronomical Society by Billiling Dullo, Alistair Graham and Johan Knapen. Their title was almost comically restrained. A remarkably large depleted core in the Abell 2029 brightest cluster galaxy IC 1101. I am putting these two results side by side because they are two views of the same object, and they only make sense together. But nobody should come away thinking one team found all of this at once. This is a picture that several groups assembled over decades, and it becomes coherent only when you lay it out flat. So, here is what is wrong with the middle of this galaxy. Start with what you would expect. When you look at a normal elliptical galaxy and plot its brightness against distance from the centre, the curve rises steadily as you move inward, brighter and brighter, all the way to a peak. More stars per unit area near the middle. Obvious. That is not what the most luminous ellipticals do. In the biggest ones, the curve rises, and then, in the innermost region, it flattens out. It stops climbing. The very centre is dimmer than the extrapolation of the outer profile says it ought to be, as though someone has taken a scoop out of the nucleus. Astronomers call these core-Circic galaxies, and they call the flattened region a depleted core. The size of the depleted region, the break radius, the distance at which the curve stops behaving normally, is typically between 20 and 500 parsecs. IC 1101's break radius is 4,200 parsecs, 4.2 kiloparsecs, plus or minus 0.1. In angular terms, 2.77 arcseconds. It is an order of magnitude larger than the top of the normal range. It is the largest depleted core measured in any galaxy, ever. The runner-up, the central galaxy of the cluster Abell 2261, comes in at around 3.2 kiloparsecs, and everything else is far behind. Measured against the relationship between core size and galaxy brightness that the rest of the population follows, IC 1101's core is 1.02 dex too big, about 3.5 standard deviations off the line. In more human units, the depleted region at the centre of this galaxy is roughly 13,700 light-years across. For comparison, the distance from the Sun to the centre of the Milky Way is about 26,000 light-years. So the hollow at the heart of IC 1101 is a bit more than half the radius of our entire orbit around our own galaxy. And now the number that I found genuinely difficult to sit with. You can calculate how much stellar mass is missing. You take the outer profile, extrapolate it inward the way it would have gone if nothing had happened, and subtract what is actually there. The difference is called the stellar mass deficit. For IC 1101, that deficit is about 4.9 times 10 to the 11th solar masses. 490 billion solar masses of stars that ought to be at the centre of that galaxy and are not there. That is roughly 8 times the entire stellar mass of the Milky Way. 8 whole galaxies like ours in missing material, absent from a region 13,000 light-years across. In terms of light, the deficit comes to about 28% of what the central bulge would have shone at before it was depleted. More than a quarter of the light of the core of this galaxy is simply gone. Let that be still for a moment. There is a region at the centre of the largest galaxy anybody has ever measured, larger than the distance from here to the middle of our own galaxy, where 490 billion stars worth of material should be, and is not. Not burned out, not consumed, not hidden, removed. Something picked those stars up and threw them, one at a time, over hundreds of millions of years, and the emptiness they left behind is still there, and it is going to be there for the rest of the history of the universe, because nothing exists that could ever put them back. The largest single structural feature in the interior of any known galaxy is an absence. So what did it? The mechanism is called core scouring, and it is one of the more elegant pieces of galaxy dynamics. When two large galaxies merge, each of them brings a supermassive black hole. Those two black holes sink toward the centre of the merged system by dynamical friction, the same drag that brought the galaxies together in the first place, and eventually they find each other and settle into a bound orbit, a binary black hole at the centre of the new galaxy, orbiting each other, and then that binary starts to clear the room. Any star that wanders close enough to the pair undergoes a three-body gravitational encounter. The mathematics of three-body interactions is famously unsolvable in closed form, but the statistical outcome is well understood. The lightest object tends to leave with extra energy, and the heavy pair tighten. So the star gets slingshotted outward, sometimes clear out of the central region entirely, and the binary's orbit shrinks by a tiny amount. Then it happens again, and again, hundreds of billions of times, over hundreds of millions of years. If you want an image, think of a lawn sprinkler, a spinning pair at the centre flinging everything that comes near it outward in all directions. Except the sprinkler runs for 300 million years, and what it is spraying is stars. The end state is a nucleus that has been systematically emptied out to a radius that depends on how massive the black holes were and how many mergers there have been. So run that logic backwards, and you can weigh the black hole from the size of the hole. Here is how the arithmetic is supposed to go. Each dry major merger, each time this galaxy swallowed something comparable to itself, should produce a mass deficit of roughly 1 black hole mass. So if you divide the total observed deficit by the black hole mass, you get the number of major mergers. Dullo, Graham and Napen estimated the black hole mass the standard way, from the scaling relations that connect black hole mass to a galaxy's velocity dispersion, luminosity and stellar mass. And they got a ratio of deficit to black hole mass of between 38 and 101, which implies at least 76 dry major mergers. Their own description of that number, in the paper, is that it is excessive and unrealistically high, and it is. 76 major mergers is not a thing that can have happened. There are not enough comparable galaxies in a cluster to eat 76 of them, and there has not been enough time since the universe began to do it in. Something in the calculation has to be wrong. Their conclusion is that the wrong input is the black hole mass. If the core was carved not by a normal supermassive black hole binary, but by an unusually large one, the numbers come back into range. Specifically, they estimate a final coalesced mass of between 4 and 10 times 10 to the 10th solar masses. 40 to 100 billion solar masses, which is between 1.7 and 3.2 standard deviations above what the galaxy's own properties predict it should have. Now, and I want to be as clear about this as I can, that is an inference. It is not a measurement. Nobody has watched stars orbit this black hole. Nobody has seen a shadow. Nobody has timed an orbit. Nobody has measured a rotation curve in its immediate neighbourhood. Its mass is deduced from the size of the hole it appears to have dug, by an argument that assumes we understand the digging correctly. It is a reasonable inference, and it is the best available, and it is still an inference. Every time you hear that number quoted, that caveat should come with it. But if it is right, it puts this object on a very short list. Sagittarius A star, the black hole at the centre of our galaxy, is about 4.3 million solar masses. This one, if the estimate holds, is between 10,000 and 23,000 times heavier. If Sagittarius A star were a marble sitting on a table, this would be a sphere about the height of a person. Its event horizon would be roughly 600 astronomical units in radius. An astronomical unit is the distance from the Earth to the Sun. Neptune orbits at 30. So the boundary of this thing would be about 15 times further out than Neptune, a sphere of no return comfortably larger than the entire planetary region of our solar system. And there is a theoretical ceiling on this. Above somewhere around 50 billion solar masses, the argument goes, a black hole cannot keep feeding, because the accretion disk that supplies it becomes so massive relative to the hole that it fragments under its own gravity and turns into stars instead of falling in. The upper end of the IC 1101 estimate sits above that ceiling, which is part of why the number is interesting, and part of why it should be held loosely. And here is the last thing about it, and it is the part that I keep coming back to. It is silent. There is no active nucleus in IC 1101, no quasar, no blazing accretion disk, no visible jet tearing across the sky. Whatever is in there stopped eating a very long time ago, and it has been sitting in the dark ever since. So picture it, and take your time. A sphere of absolute blackness 600 astronomical units across, larger than our entire solar system out past the Kuiper Belt. No disk glowing at millions of degrees, no roar of radio emission, nothing falling in. It is not doing anything. And around it, for thousands of light years in every direction, is the stellar desert it made, the region it emptied star by star and then outlived. The tidal forces at the edge of a black hole that large are gentle. This is counterintuitive, and it is true. The bigger a black hole gets, the weaker the stretching at its horizon becomes, because the horizon is further from the centre. At 100 billion solar masses you could cross the boundary and feel absolutely nothing. No tug, no warning, no sensation of any kind. You would simply pass through a place, in perfect darkness and perfect silence, after which there is no route back out, at the centre of the largest galaxy anybody has ever measured. There are two more details worth adding, both of them slightly unsettling. The first is that when the two black holes finally merged, they would have radiated gravitational waves asymmetrically, and that asymmetry delivers a kick. Merged black holes can be launched at hundreds or even thousands of kilometers per second. If the kick is not quite enough to escape, the black hole oscillates, falls back through the nucleus, out the other side, back again, scouring the core a little more on every pass. That may be part of why this core is so much larger than anyone can otherwise account for. The second is that the very centre of IC 1101 does not have one light peak. It has two, a double nucleus, which might be a recently swallowed galactic centre that has not yet settled, or might be a black hole sitting somewhere it should not be. And notice what all of this adds up to. The same process, the long, patient chain of dry mergers that built this galaxy outward to 260 kiloparsecs, is the process that hollowed it out at the middle. The largest structure in the known catalogue of galaxies, and the largest absence in it, are two ends of one mechanism. It grew by eating, and eating is what emptied it. Which raises an obvious question. If everything about this object is the signature of collisions, when was the last one? The answer is that it has not finished yet. Part 12. The cluster is still ringing. For most of the last half-century, Able 2029 had a reputation, and the reputation was boring. I mean that as a technical compliment. In X-ray astronomy, clusters come in two broad flavours. Some are obviously disturbed, lopsided, lumpy, with visible shock fronts and bright knots and gas piled up on one side, the unmistakable wreckage of a recent collision. And some are relaxed, smooth, symmetric, circular contours, a bright settled core, everything where it should be. Those are the ones you use as control cases, the ones you calibrate against, the ones you point to when you want to say what a cluster looks like when nothing is happening to it. Able 2029 was the archetype of the second kind. beautifully round, a strong, quiet, cool core, a cluster that had, to all appearances, finished being built a long time ago and settled down. That reputation has been dismantled in 3 stages, and each stage found the disturbance bigger than the last. Stage 1, 2004. Tracy Clark, Elizabeth Blanton and Craig Sarrazin published a Chandra X-ray study of the cluster's cooling core, and inside the smooth, relaxed-looking system, they found something that should not have been there. A dipolar spiral excess, a curl of brighter, denser gas winding clockwise out from the core to a radius of about 150 kiloparsecs. They measured about 6 times 10 to the 12th solar masses of gas in the excess, 6 trillion solar masses of hot plasma, arranged in a spiral in a cluster that was supposed to be featureless. Stage 2, 2013. Rachel Paterno-Marler with Blanton, Scott Randall and Clark went back with deeper Chandra observations and followed the same structure further out. Not 150 kiloparsecs, 400. At the time, it was the largest continuous spiral of this kind observed in any galaxy cluster anywhere. Stage 3, 2025, a 485 kilosecond Chandra observation. That is 135 hours of exposure on one object, one of the deepest X-ray stares ever taken at a cluster, traced the spiral out to nearly 600 kiloparsecs, one of the longest, most continuous structures of its kind ever seen. And they found more, a broad splash of cooler gas off to one side and evidence for a merger shock. So what is this spiral? What makes a cluster do that? The phenomenon is called gas sloshing, and the name is unusually honest. Picture a bowl of hot soup. It is sitting still. Now take a spoon and pull it through the soup, off-center, not stirring, just one displacement, one shove to one side. And then take the spoon out and leave the bowl alone. The soup does not stop. The liquid you displaced falls back toward the middle, overshoots, sloshes up the far side, comes back, and because your shove was off-center, the whole thing is now rotating slightly, so the sloshing does not just go back and forth in a line. It winds, it spirals outward, turn after turn, and it keeps going for a long time after the spoon is gone. Now replace the soup with the densest, coolest gas at the center of a galaxy cluster, a cloud 100,000 light-years across at 90 million degrees, and replace the spoon with an entire subcluster of galaxies falling past on an off-center trajectory. The subcluster's gravity tugs the cool core sideways as it goes by. Then it leaves, and the core sloshes. Each arm of the resulting spiral is bounded by what astronomers call a cold front, a sharp surface where denser, cooler gas sits directly against thinner, hotter gas, with the pressure roughly continuous across the boundary. That is the opposite of a shock wave, where the pressure jumps. Cold fronts are contact surfaces, not collisions, and the fact that they stay sharp for billions of years, that the two gases do not simply mix, tells you something about magnetic fields and viscosity in the plasma that is still being worked out. Markovich and Viklinin's review of shocks and cold fronts is the standard reference, and it is a genuinely fascinating piece of physics in its own right. The important thing about sloshing, for our purposes, is that it is a fossil. It is extraordinarily long-lived. A cluster can look perfectly relaxed at large scales and still be sloshing internally from a shove it received billions of years ago. And in this case, the 2025 team put numbers on the shove. They compared the observed structures, the 600 kiloparsec spiral, the cool splash, the possible shock, to simulations of an off-axis merger with a mass ratio of about 1 to 10. What matches is not a first encounter. It is the relic of a second core passage of the intruding subcluster, roughly 4 billion years after the merger began. The splash of cool gas is a wake, a trail of material dragged along behind the thing that came through. It is worth pausing on what a 1 to 10 mass ratio means here, because the word merger suggests two equals colliding, and this was nothing like that. Abel 2029 is a quadrillion solar masses. A tenth of that is 100 trillion, which is still an entire group of galaxies, a system larger than the local group we live in, arriving at something like 1,000 kilometers per second. That is the object that grazed the core. It was relative to the cluster a small thing, and a small thing was enough to set 600 kiloparsecs of plasma, ringing for billions of years. The timing is worth holding on to too. The disturbance we are looking at now is the second core passage, 4 billion years after the encounter began, and the material has been redistributing itself ever since. Depending on which part of the structure you point at, You are looking at something that was set in motion somewhere between 2 and 4 billion years ago. On Earth at that time, the atmosphere was only just becoming breathable. The wave has outlasted the entire history of complex life here, and it is not done. Their own summary of it is the line I keep thinking about. Able 2029, they wrote, is still settling from past interactions, showing that even the initially most relaxed-looking clusters can be hiding a rich history of dynamical activity. The one that looked like nothing was happening. 600 kiloparsecs of 90 million degree plasma still ringing. There is a nice detail that came out of the same work. At the centre of IC1101 there is a radio source with 2 lobes, and those lobes are bent, swept back into a shape astronomers call a wide-angle tail. For decades, the standard explanation for bent radio lobes was that the host galaxy is moving through the gas, and the gas pushes the lobes backward the way running pushes your hair back. But IC1101 is not moving. We established that earlier. It sits at the kinematic centre of the cluster, within the uncertainties, motionless. So the 2025 analysis concluded the opposite. It is not the galaxy moving through the gas, it is the gas moving past the galaxy. The lobes are not swept-back hair, they are windsocks, hanging in an intracluster breeze, and the breeze is the slosh. And now the circuit closes. Because remember what else the 2026 imaging paper reported, alongside the edge. They found a large number of asymmetrical, very low surface brightness features scattered around the galaxy. And those features, they write, are spatially consistent with the large-scale disturbances observed in the intracluster medium through X-ray studies of the cluster. Those features are made of stars, 2 completely independent components of this system. The hot plasma, seen in X-rays by an orbiting observatory, and the faint starlight, seen in visible light from a 2.5-meter telescope on a volcano, are showing the same disturbance pattern in the same places, which means the collision that set the gas sloshing did not only move gas, it moved stars. The outskirts of IC1101 are asymmetric because something came through, and the stars out there are still riding the wave. Put yourself out there one more time. You are in the outer regions of the galaxy, hundreds of thousands of light-years from the centre, among stars so sparse you could go a lifetime without noticing another one. And everything around you, every star in this region, and 600 kiloparsecs of gas at 90 million degrees that you cannot see at all, is swinging, slowly, on a timescale where one full oscillation takes longer than the whole history of multicellular life on Earth. You would never feel it. Nothing here moves fast enough to feel, but the entire outer body of the largest galaxy in the known universe is a wave that has not finished breaking, from a collision that happened before there were flowers on this planet, and it is still going. This is also, as it happens, exactly why the measurement had to be done the way it was done. Remember that the team measured their profiles along many separate position angles, instead of averaging in circles around the galaxy. Now you can see why that mattered so much. If they had averaged, these asymmetric features, the very things that connect the starlight to the X-ray structure, the evidence that this galaxy is in motion, would have been folded into the mean and erased. They would have got their edge. They would have missed the fact that the galaxy is still being assembled. Which brings us to the number, and to what it actually is. Because if the outskirts of this galaxy are still moving, still being fed, still asymmetric from a collision that has not settled, then 260 kiloparsecs is not a fact about the universe. It is a snapshot. Part 13. How large can a galaxy be? So, how large can a galaxy be? I promised you an answer, and here it is, in 3 parts, and I want to give them to you in order, because the order is where the interesting thing lives. The first part of the answer is the plain one, and it is not the part that defies explanation. 1.7 million light-years, 520 kiloparsecs, 3.4 trillion solar masses of stars. That is the largest galaxy anybody has ever properly measured, and it is smaller, considerably smaller, than the number that has been circulating about it for 35 years. The record shrank. That is what happened. The most famous galaxy size in astronomy was cut by more than half, and if you came into tonight expecting a video about a new record being set, what you actually got was a video about a record being corrected downward. And I want to argue that the shrinking is the discovery, because for the first time the number means something. 6 million light-years was a radius, doubled, under a dead value of the Hubble constant, applied to a glow that its own measurers refused to assign to the galaxy. 1.7 million light-years is the distance at which the density of stellar mass drops, because there was never enough gas beyond it to build a star. The first number was a decision. The second is a place. The second part of the answer is where it starts getting strange, because what actually defies explanation is not the size. It is the pileup. Look at what this one object is holding simultaneously, the largest edge radius ever measured for any galaxy. Among the largest stellar masses known, the largest depleted core ever found, by a full order of magnitude over the runner-up, a hollow 13,000 light-years across with 490 billion suns worth of stars missing from it. And, inferred from that hollow, a black hole of 40 to 100 billion solar masses, which sits at or beyond the theoretical ceiling for how large a black hole can grow by feeding at all. Every one of those is an extreme. They are all in the same galaxy, and there is no theory that predicts a maximum for any of them. That is worth stating flatly, because it is easy to assume that somewhere in a textbook there is a chapter explaining how big a galaxy is allowed to get. There is not. What there is instead is a set of plausible breaks, none of which has been shown to be the one that actually stops things. Break 1 is fuel. IC 1101 makes no stars. It has no cold gas left worth speaking of. Everything it gains from here, it gains by swallowing something that already exists, which caps its growth at the rate at which neighbours arrive. Break 2 is the one this whole video has been circling. As the central galaxy grows, the material it acquires at large radii is increasingly held by the cluster rather than by the galaxy. Past a certain point, adding mass does not make the galaxy bigger. It makes the glow between the galaxies brighter. So the maximum size of a galaxy might not be a property of the galaxy at all. It might be a property of the cluster it lives in, and specifically of the radius at which the cluster's gravity takes over. Which is a genuinely strange thought, that the biggest thing a galaxy can be is set by the thing it lives inside. Break 3 is simply time. Dynamical friction gets slower the smaller the infalling galaxy is, and the wider its orbit. Out at the edges of a cluster like Abel 2029, a small galaxy may need longer than the current age of the universe to spiral in. The central galaxy is not limited by appetite. It is limited by the delivery schedule, and the universe has only been open for 13.8 billion years. And then there is the fourth possibility, which is the honest one and which the paper's own framing quietly points at. The limit may not be physical at all. It may be observational, because every rival to this galaxy fails on measurement, not on physics. Not one of them has been imaged this deep. Not one has had the extended point spread function work, the 250 subtracted stars, the mass density profile at multiple angles. There may well be larger galaxies out there. We have exactly one properly measured data point at the top of the entire distribution, and one point is not a distribution, it is an anchor, and that is a solvable problem which is the genuinely hopeful part of tonight. The technique now exists and it has been demonstrated at the hardest possible target. Somebody can point the same method at ESO 38376, and at ESO 306-17, and at ESO 44446, and at every other object on the list, and in a few years we will have not one anchor point but a dozen. Wide-field surveys built for exactly this kind of faint, extended, low-surface brightness work are coming online now, and they will produce images at these depths across large fractions of the sky, rather than one galaxy at a time. The ranking that has been argued about for 35 years is about to become an actual measurement for the first time, and it is entirely possible that IC 1101 loses. If it does, that will not undo anything in this paper. A ruler does not become wrong when it measures something bigger. Which brings us to the third part of the answer, and this is the one I've been holding. It is still growing. The paper says so directly. Its outskirts, the authors write, show clear signatures of ongoing mass assembly, indicating that its spatial extent is still growing. Those asymmetric features in the faint outer light, the ones that line up with the sloshing gas, that is not scar tissue. That is a meal in progress, and it gets more specific than that. A detailed census of Able 2029 has identified two separate systems falling into it right now. Able 2033, a cluster in its own right, coming in from the north, and a previously unnamed southern infalling group. Between them they carry roughly 60% of the mass of Able 2029 itself. They are gravitationally bound, they are not passing by, and the modelling puts their arrival within about 3 billion years, with something like a 70% probability of a full merger in that window. The astronomers who did that census added one more line that I think is the quietest and most remarkable thing in this entire story. The accretion rate, they wrote, is larger than the average predicted by simulations. This system is eating faster than the models say it should be able to, so the largest galaxy anybody has ever measured is not a finished object. It never was. Remember what I said much earlier about galaxies like this, that they are not things that formed and then sat there, that they are processes still running. That was a general statement about a class of object. Here it is with a date attached. In about 3 billion years, 2 more systems arrive, and this galaxy gets bigger, and the number we just measured stops being true. We did not photograph a monument. We photographed something mid-meal. And I think that reframes what the word edge even means here. Because 260 kiloparsecs is not a wall, there is nothing there. No barrier, no membrane, no boundary in any sense you could stand at and touch. What is there is the outcome of an argument. The place where this galaxy's gravity finally loses to the cluster it lives in, where a star stops belonging to the object and starts belonging to the crowd. And that argument is not settled. It is still being had right now at a distance of 1 billion light-years, in silence, and the line moves. 3 astronomers in 1991 looked at the same problem and wrote that the distinction was a matter of semantics. They meant it as an admission of defeat. 35 years later, the semantics turned out to be the whole thing, because the question of where a galaxy ends was never a question about a telescope. It was a question about what we meant. Solve the meaning, and the measurement follows. So here is where all of this lands. What scientists just discovered about the largest galaxy in the universe genuinely does defy explanation, but not in the direction anyone expected. The size is not the mystery. The record is smaller than the legend. What defies explanation is that this one object holds every extreme at once, that nothing in our physics says why it should stop where it does, that the black hole at its heart may be larger than a black hole is theoretically allowed to become, and that after 10 billion years of consuming its neighbours it is still, right now, not finished. Somewhere out there, 1 billion light-years away, in a patch of sky in Virgo where there is nothing to see, an object 17 times the width of our galaxy is drifting at the bottom of a gravitational well, with 2 more clusters falling toward it. The light we measured tonight left before there were animals with spines on this planet. By the time it stops growing, if it ever does, everything we have ever built will have been gone for an unimaginably long time, and the number will be wrong again. The difference is that this time we will know exactly why.